Good morning, good evening and good afternoon, whichever is currently applicable in your time zone. Today we will be starting with the generation 6 of my codebase. I will be explaining almost all of it step by step while designing it from ground up. One thing that I will not be explaining in detail will be how combat systems work, and the second part that I will not be explaining will be how scout behavior works. These two will use extremely hacky behaviors, and as such they would be a bit difficult to explain while keeping the core idea of teaching rather than showing exact solutions as the only solution worthwhile. Anyway, let us begin. Our core and our foundation of basically entire generation 6 will be communications. As such, we will start with basic communication. As you are aware, we can modify signals from behaviors. However, most of you will be aware of that signal can send only one set of data at a time. For example, one laser mining tool, or 20 metal bars. However, that's not entirely true. What we will be doing is we will try to push more than one piece of data within a single signal. In fact, we will be using item types or references to the objects, like here, as icons rather than element that we want to send, or as specific signal. And we will also use value completely in different way than you are used to. First things first, for example, if we were to send two pieces of data, say, as I've shown you, 20 iron bars and 1 laser mining tool, we will be able to do it in this way. 21, as in 20 and 1. We will also be able to send it in this way. 20, 0, 1. And if we were to add third part, for example, let us assume that we will check how much metal ore we have, how much crystal chunks we have, and how much silica sand we have, we will be able to send it in, for example, right now we will have 0, but if we had 10 of each, we could send it in this form. We will be using for that simple division, or rather advanced division, and modulo operation. For our purpose, we need to know that to extract, for example, 2 digits, we need to select highest value that we can represent by these 2 digits and add 1 to it. In our case, we will divide by 100. I did say it in a bit odd way, as that's basically the number of digits, power of 10 to the number of digits, but the distinction that highest value that we can represent with the digits we have, plus 1, will be important, as generation 6 will operate in binary code. Anyway, without further ado, let us first allow us to encode data in, well, decimal. So let's assume we want to add 3 numbers. They will be the 3 parameters. I will call it encoding example. So what we want to do? First, we will make sure that parameter 1 will be the first, parameter 2 will be second, and parameter 3 will be third. The data that we will work will go from 0 to 100. What we can do here is we can do the following trick. First, we will multiply the first parameter by 1000. Remember, our values will be from 0 to 100, so we need 3 digits So we take the largest number that we can represent by these 3 digits and add 1 to it. That's 1,000. So we multiply it by 1,000. Let me quickly reset it, as frankly I don't want the coordinates to be represented here. And we will add result as a signal. We'll modify the signal all the time as it saves us on number of variables we use. And given that entire behavior is processed before next behavior is analyzed, we can do it safely. What we will now do is we will now add to the signal the value of parameter 2 and save it as a signal. Next step will be to multiply the signal by 1,000. And final step will be to add to the signal value from parameter 3. Oops. You may notice that we are using initial parameter here. However, this is the same as if we added parameter 1 to basically nothing. Sorry, we added nothing to parameter 1 and saved it as a signal. To save on instructions, I did it this way. So, let us start it, and for example, let's add the following values. These values can be anything from 0 to 1,000. We'll start it up and we can see how it behaved. However, you may notice that we're having a small glitch here. Why is it? Well, we're processing each step all the time. So let me quickly add wait instruction. So once we processed it, we're done. Okay, so let's analyze this value that we have here. Last 3 digits is 44. Next 3 digits is 55, and the first 3 digits is 100. Let's make it so it takes only 1 tick. Well, first we remove wait ticks here. We add wait tick here. And we unlock this behavior. And as you can see, the result is the same. Now, why is it useful? Well, let's create a behavior controller second and add a decoding example. We will add the source as the last option. Usually, we'll be using the signal register. Actually, we can use signal register as our source, as that's what it is. First, I will unlock the behavior and add wait 1 tick. This will be basically every single of our behaviors will start with those 2 elements. Well, there will be another one, but to that we will go later on. So, first things first, we have our signal. What we now need to do is we need to extract the first value. Let's start with the same order. So we want the parameter 3 to be 44, and that will be the first thing that we extract. So, step 1. We need to divide our signal by 1,000. We are doing basically what we did in the opposite direction. However, we don't want to modify the original source, so I will create a variable a. What we will now do is we will multiply it back by 1,000. Now, in normal operations, normal maths, if you divide x by 1,000 and then multiply it by 1,000, it does nothing. However, the notable element is that Desynced is operating on integer values, not on real numbers. As such, it cannot represent fractions. When we divide our number by 1000, in this case, we remove everything that are in the last 3 digits. As the result, let me quickly show you how it works. I will add it here and here, just so you can compare it now. And let me finally remove this one, just to make it clearer. As you can see, this value is not equal to this value. In fact, this value lost the last 3 digits. And that's what we will use now. The third step, let me quickly return it to the original form. The third step will be to subtract from our original signal the number we have, and in parameter 3 we will have what we need. And let me quickly add here b, as that might be of use later on. So now, as we push it, we have 44 as an output, as we wanted. Let's do the same, or rather similar, to the next step, and here will be a small difference. We will now divide it by 1000 again, as we did before, and we will get this source. We don't want the full data, we want only the previous part that we extracted. And here we know we will have the first 2 signals. As we know we will have 2 signals, we can already output the original signal, the first signal here. We can now multiply the first signal again by 1000 and subtract from the analyzed signal. This now allowed us to decode it as we change the values here. Remember, we're reserving 3 digits here. We can use basically any values that are up to 3 digits. And as you can see, even if the first digit is smaller, it will still keep the nature. Now, I used digits here and the decimal system as an example. However, what we will be doing instead is using binary. So in our case, rather than, if we want to have numbers from 0 to 100, rather than using 1000, we will use 128, as that is nearest power of 2, well, smallest power of 2 bigger than the number that we need. We will be able to represent from 0 to 127. And again, we will do the same here. We will add some values here. However, I cannot add 234, as that will in fact break the encoding. So let's add 127. Now if we start it up, you can see that the number stopped being easily readable by us. However, the code still is able to read it. If we want to add more elements to encoding, we basically do the same thing that we did. Let us add 4, for example. So first we will multiply the result. We'll copy these. We'll basically copy these two elements. So add 4th. Now, one thing that we should keep in mind, however, is that 127 is a power of 2. We have a limit to the number of bits that we have. Luckily, 127 isn't that high of a power of 2. Give me a second. That'd be 2 to the power of 7. So we can add quite a few numbers. We have 31 bits that are meaningful. So for values from 0 to 127, we get 7. Actually, 4 might be the limit here. As it's 31. Yes. These 4 digits, these 4 numbers is the largest amount of 7-bit numbers that we can fit in this encoding. Nonetheless, let me add here parameter 4. Now, this part will basically stay the same all the way up here. We first have to extract parameter 1. So we will do it this way. First, we remove this one. Now, we will now change it a bit, and let's take care of parameter 3 first. So we will divide it using A as our source. A will be basically the rest of the code that we haven't touched yet. We'll divide it. We will multiply it. And we will subtract it. That's B. Give me a second, as I think I made a small mistake here. Yes, we will need to add C here, as A will otherwise be corrupted. Then the result will be parameter 3. So we will basically swap between A and C as the number we will work with. So now we will divide C by 128, and this is the place where we already knew we can save it, as that's second to last. And subtract C, B, 2. Okay, let's try it. Yep, and as I've said, it works. This will be the first of our methods. I call it, well, this is basically signal multiplexing. It's not that I call it signal multiplexing. So encoding is multiplexing, decoding is demultiplexing. There will be, however, one more trick that we will use basically for the same use. Now, I will add cycling. We know how we can cram more data into single signal, but now I will show you how we can swap between multiple values in the single signal. Now, the catch is we cannot set more than one reference to the entity. So basically, if we were to target, we call target 1, target 2, and target 3, we cannot target 3 different entities and send all of those 3 entities in the single tick. Let's make sure we can do it in 3 ticks instead. The most common solution to this problem would be to add, for example, radio senders and radio receivers. We will do it by moving through these signals one after another. So, the first step is to cycle those. I will call it data cycling. Okay, so first we need to unlock the behavior. Next, we will perform only one operation at a time. And the next step will be something like this. We take variable a, which starts at being nothing, and we add 1 to the value and output it here. What we will now do is we'll compare whether a is bigger than the number of signals we want to send. In this case, it will be 3. Okay? So, if it's up to 3 or smaller, we'll call a small subroutine, which we will call send signal at ID. Luckily, our signal ID will be quite simple. It will basically be integer. Technically, I will only use it as a call for now, just as a placeholder. However, if the value here is higher than that we have, we need to reset it. So what we will do is we will set it at 0 and reset it. Well, we could also do it a bit more standard way, which is also fine. Okay. Now let me quickly add 2 more calls to the same subroutine, as it will save us some time. We'll add 2 inputs, signal and ID. Let me quickly set it. Here we are basically going to the highest ID we have, and we move it here. I'm using it this way as while we could call from subroutine the specific parameter, I want to be able to send signals that are not set in parameters. So, we have parameters here, so let's take care of our signal. We don't need to unlock it here. We already have the entire behavior unlocked. What we now do is we need to... Right, I forgot to add one more thing. A clock. What I call a clock is basically the a variable. What we now want to do is we want to compare whether clock is the same as our ID. If it is, we will set number. Sorry, I said if it is. We'll get the signal. We will set the number and set it to the signal. We can also add keep if empty check. So, let's do it as well. if the signal is empty, well, if it's different than we are doing what we did. If the signal is empty, however, we'll check if its value is also empty. If it is not equal to 0, we will send it as it is. However, if the signal is basically empty, so it has no icon, if we're using that term, and its value is 0, what we will do is we will increment the clock. And I by accident moved it here. Okay. So now we've skipped this slot. So what it will now do, on the first tick, once it's initialized, it will check that variable a is empty, and it will make the variable a equal to 1. Then it will compare whether a is larger than 3. It is not. And what it will do, it will try to send a signal. The signal ID here is 1. If this parameter is empty, it will change the clock to be 2 and will go on. Either way, during this subroutine, it will check if our clock is equal to the ID of the signal. If it is, it will process it as it is. If it is not the same clocks as it is ID, it will basically ignore this signal. If the clock is equal to ID, it will check if it is empty. If it is empty, it will basically say, well, we have nothing to do here, let's move to the next signal. Otherwise, it will set the signal with ID. Let me show you how it works in practice. As you can see, the code now sends 3 signals, one after another, as it basically cycles. If there is no element, you can see that the element is ignored. Unfortunately, when all 3 of them are empty, we unfortunately cannot do much about it except for giving it other data. Unfortunately, this doesn't work with world coordinates, as that's not what we allow it to do. We do not check whether world coordinates are interesting to us. However, we can send any other icon for our purposes. What this code does not allow us to do, however, is it does not allow us to add more data. It's fine, really. Anyway, we know how to send it, so let's analyze how to receive it. I'm gonna grab as count. And just to make sure you can see that I'm not doing any tricks here. And what we will do is we will set the following. We'll select a source. We'll get signal ID 1, we'll get signal ID 2, and signal ID 3. As I said, we start by unlock and wait 1 tick. Okay. What we now want is a new subroutine, get signal at ID. We want source, we want signal ID, and we want output. What I will now do is I will call it passive read. Basically, it will not wait for a signal. However, I will also create an active read shortly. So, first things first, we create 3 copies as we have 3 signal IDs. And I will order them in the opposite order. Now, unfortunately, we first have to add some copy all the way to output, as otherwise it won't be recognized as valid output. Okay. So, we get edit, and what we want to do is now the following. First, we're going to read signals from source. The result will be A. Next step is we will compare number between signal ID and the signal ID basically from the signal. What we will now do is we will strip the signal of its value and we will output it here. If it's larger or smaller, we completely ignore it as that's wrong ID. Simple as it gets. And let's see if it can read it if our source is command center. Well, there's signal ID 3. As we forgot, signal is indeed 3, as we forgot to add signal cycling. Which one is it? Here. And as you can see, it read correctly our signals. If we were to change, for example, this to dropped item, we can see that our scout can recognize it. Now, why did I add it in opposite order? I will make sure that command center is still cycling it. It is. What I will do now is create a variation for this passive. Rather than passive, what we will now do is we will basically wait for the signal. We will not, we will not process it further. We'll simply wait. It may be and let me quickly rename it to active read. It may be useful if you're looking for a specific signal and you need it to process in the behavior. Most likely in our 6th generation we'll be using passive reads, but let me show you that it does indeed read it in the order that we want it. Okay, so now that we have signal reading, encoding and decoding, we will be able to start working on something more interesting in the next video, as that one is getting slightly complex already. Now, if you have any questions to why any of these elements works as it is, or why I chose to do it that way, let me know. I will also quickly show you that we will be able to use Actually, I think 126 is the correct. Yes, 128 is the correct. Anyway, I want to show you that if we were to use smaller values, we will be able to cram more data into it as well. So for example, if we were to make 4 values at from 0 to 7, we can do it in the same way. And as 0 to 7 is using less bits, we can cram more data here. During our operation, I will most likely be using more generic decoding example. I guess I will add a variant to it, in fact. As a subroutine. In fact, given it is part of our current talk and topic, let me quickly create a subroutine that we will be using that's slightly more generic. Now, I will add source. I will now add remainder, and I will add data. However, I've just realized I need to add a divisor. In fact, I will quickly add this to description that divisor is smallest power of 2 larger than largest possible value to send. And I will add both encoder and decoder at the same time. So let me quickly load it up. Okay, so first we need to encode it. Source, in this case, will be signal that we're working with currently. I will quickly clean it up. As this is going to be subroutine, I will remove the unlock. So, source, or signal, divisor, in this case it will be multiplier, data, and what else we need? Actually, I think that's all. Original signal, divisor, input, and output. Okay, so signal will be doing what we already have, divisor will be how many bits we need, input is what we want to add, and output will be what we're outputting. How it will work, I will show you in a minute. So, first things first, we have a signal. We want to multiply the signal by the divisor, just to move it a bit. And then we simply add the final piece of data. It's simple, but it's useful. Let me quickly copy it to clipboard, clean it up, and call it as a subroutine. And add 3 more, or 4 more in this case. I will make it so it's 5 parameters instead of 4. So I'll call it 4 times. Now, the initial signal is nothing. The divisor will also be nothing. So what we can do instead is, rather than using 5 of the encoders, we can grab first parameter. And again, let's work from 0 to, say, 15. So the nearest is 16. The input will be second one. And output will be A. Signal, we will chain it up and output here. 16, 16, and 16. In our final operation, we will most likely be using mixed values as well. Here we will unlock it and add a wait tick. Let's add here for some values between 0 and 7. We can also see that our signal gets changed every time we modify it. Okay, and let's go with decoder now. Let me quickly copy it, clean it up, and we're going to decode this 4 parameters. What we will now do is we will decode piece of data. Now, original source, we will call it signal, divisor, remainder, and output. So we have a signal, we divide it by divisor, and what we got from it is remainder. We will now multiply it by a divisor and subtract as an output. That's basically what we are doing step by step. I will add now a few more of those. Now, first things first, we're gonna get the signal, and we know that our divisor is 16. The divisor of 16 will be everywhere. We will now chain it here and as outputs. Now we have a small glitch. And I guess it's time to check why. For that, we will quickly add a few more parameters. And see how the remainder changed, or how our signal changes. And why it breaks. It seems that this one is getting modified as we want it to be. So let's check this one as well. And as some people ask me how I debug it, basically in this way. Now, as we're dividing, we expect it never to be smaller than 0, and in fact it does work as we want, at least partially. It seems that 0 breaks our data. Let's check if 1 will break it as well. Okay, so the first remainder here gets broken. Let's see why. What I will now do, as it seems to get broken on the third parameter, so here we will need to analyze how the data changes. So we're gonna get here, and I'm quickly gonna grab a few more parameters, not call, I'll use copy, P3, P2 before this change. Now I will need A, and I'm also gonna need P1 and P2 here. So first things first, I'm gonna grab the third call, and I'm gonna output every additional piece of information here. Okay. So, let me grab my notepad and see what is going on here. This is the one that breaks it, as this one should be 4 instead. Five, 6, 7, 8, 9. In the meantime, let me quickly pause it and debug it, as I guess myself mumbling to myself might be a bit boring. Be right back. Okay, it seems that this code as we have does tend to have a minor issue when it's changed all the time. So rather than using it as a full chain here, we will add a break between them just to avoid some errors. So if we are to add more pieces of the data, we will basically weave A's and B's instead. So that's how we will do it, and I guess that'd be all for today. As I've said, if you have any questions, feel free to ask. If you have suggestions, please let me know. Next time, I guess we will start working on something more interesting. In our case, it will be, I think, an automated factory. It will be a factory that will expand itself. However, I'm not sure if we will be able to finish it at one run, and as such, I guess it will be the first episode of it. Anyway, have a great evening, day, or morning, whichever is applicable in your time zone, and have a great day.